In this video, we're going to continue to talk about the non-degenerate perturbation theory, but in this specific video, we're going to go into the first order theory, and more specifically, the energy. So before we begin, we want to briefly look at what we did in my previous video, which is I generally talk about the concept of perturbation and what it does, and we can look at, for our lowest order here, we have our unperturbated system, and for first order and our second order are our approximation to the perturbated system, right? And in this video, we're going to specifically examine the first order correction, or the first approximation to the perturbation. So let's write down our equation for the first order, which is going to be h0 psi 1n plus h prime psi 0n is equal to e0n psi 1n plus e1n psi 0n. And we can first quickly just look at the formula and sort of define the variables here in case, just to do a refresh of our memory, right? So our h0 here stands for the unperturbated Hamiltonian. Our psi 1n0 stands for the first order correction to the wave function of the perturbated system, or the first approximation. And our h prime here stands for the perturbated Hamiltonian. Our h0n here stands for the unperturbated wave function. Our e0n here stands for the energy difference of the unperturbated system. And our E1n, which is what we're trying to find in this video, stands for the energy difference between the unperturbated system and the first order correction of the, or first approximation of the. It's like when you have an unperturbated system and you make a one perturbation, then this E1n simply tells us the energy difference between our unperturbated system versus the sort of first perturbated system, if that makes any sense. It's like the first order energy correction. So our E1n is the first order energy correction, and it represents the shift in energy due to perturbation. So unperturbated versus perturbated, and the energy difference between them, and we're talking about first degree here, which is what E1n is going to be. And if you still kind of think it's not as intuitive, just be patient and wait a little bit. We'll get into an example very soon, and you will see what this means very quickly. But first, to derive the expression for E1n, we want to first take the inner product of our equation. So take inner product of this equation with psi 0n, which is the unperturbated wave function. So mathematically speaking, that's going to look something like this. So psi 0n h0 psi 1n plus psi 0n h prime psi 0n is equal to e0n psi 0n psi 1n plus e1n psi 0n psi 0n. And you might be wondering why, like when I take the inner product, I'm able to take this out. It's because, well, E0 and E1n are both scalar, so they're energy, right? So they're both scalar, so they're a number, so we can take them out. Rather, compared to if you look at the case of our unperturbated Hamiltonian and our H prime, we can't take them out, right? Because they're not a constant like E1n and E0n are. So this is the equation we get after taking the inner product of our original first order correction equation with psi 0n. And specifically, we're going to take a look at the first term. So our first term has psi 0n h0 psi 1n. And h0 here represents the unperturbated Hamiltonian. And something very important about the unperturbated Hamiltonian is that it's Hermitian, means that its complex conjugate is just the same as its original. Right, so that means that we can move our h0 to the other side. So this is going to become h0 psi 0n psi 1n. And now we have this, right? If you recall from the Schrödinger's equation, h psi is equal to E psi, right? So in this case, we can replace our, so E0 psi 0n is just going to be E0n psi 0n, right? So this is basically the lowest order, the unperturbated solution, or the unperturbated Schrodinger's equation is, or the equation that we have here from my previous video, right? So we can change our H0 psi 0n to this. So this becomes E0n psi 0n psi 1n, and then E0n is energy, so we can take it out, so psi 0n psi 1n. So this is what our first term has become. And if you really look at the equation, you can see that we already have a term here. So these two are exactly the same, so they cancel each other out. And what we're really left with is psi 0n h prime psi 0n is equal to E1n psi 0n psi 0n, right? And this is just going to be 0n psi 0n, right? So this is just going to be 1 due to the normalization property. So we just have 1 here. So basically E1n, or the energy difference between unperturbated system and the perturbated system, is going to be E1n is going to be psi 0n h prime psi 0n. So what does this imply? It says that the first order correction to the energy is the excitation value of the perturbation, right? This is the excitation value of our perturbated Hamiltonian. And our E1n stands for the first order correction to the energy, right? The first approximation. And in my example, you can really see what this means. So in my example, I'm going to use the infinite square well. So if you recall in earlier quantum mechanics, when we dealt with infinite square well, you have a diagram like this, x, and then Vx, right? And then A here, and then the particle exists within the well where it cannot exist outside of the well. So this is what we call it unperturbated. So the wave function for this unperturbated infinite square well is going to be psi 0n, right? Is equal to square root of 2 over a psi sine m pi x over a. So this is what we're going to have here, right? And psi n0 obviously stands for the unperturbated wave function. So right here, we're gonna perturbate the system by raising the floor of the well. So this is gonna become, we're gonna perturbate it by, so same diagram. So x a v x. But in this case, we're gonna perturbate the system, or raise the floor by a constant amount, which we call v0. So this is how much we have lifted it off the floor. So the particle can only exist within this region now. So what exactly does that do to the energy, right? So E1n in this case, which stands for the energy difference between our unperturbated system 1 and our perturbated system 2. So that's what E1n stands for in this case, is the energy difference between these two. And according to what we have derived, E1n is equal to psi 0n h prime psi 0n, right? And what is our h prime here? Well, our h prime stands for the perturbated Hamiltonian, and the perturbated Hamiltonian in this case would simply be v0, right? Because that is the change, the energy change we made to the system. So our perturbated Hamiltonian is just going to be how much we raise the floor by, which is v0. So E1n now becomes psi 0n v0 psi 0n, right? And since v0 it's some constant value which we raise the floor by, is a scalar, so we can take it out of the inner product again. So we obtain psi 1n is equal to v0 psi 0n psi 0n, right? And then this is just going to be 1, right? So our E1n is going to be V0. How surprising? Well, it's not surprising at all, right? Because if E1n stands for the energy difference between these two systems, then obviously the energy difference between these two systems are just how much you raise the floor by, right? Which is V0 in this case. So that's very intuitive. So E1n turns out to be V0, which is so that implies the energy difference in this case between our unperturbated system and the perturbated system where we raise the floor by V0, which is the result of that is just going to be, or the energy difference is just going to be how much you have have raised the floor, right? So that's pretty intuitive. So this video gives a sort of gives you an idea of what U1n stands for and the formula and sort of how we come up with it. But we're just talking about U1n here. And in my next video, we're gonna more specifically look at this term, which is psi1n, right? Because we know psi 0 and we know h0, and we're giving you it's like in this video the purpose is to find U1n. So in my next video, we're gonna look at what happened to the wave function in the first order correction. And if you guys have any questions, feel free to leave the comment down below. But if not, I'll see you guys in the next video.